In 3.1, we started out with just being introduced to different types of functions. We just learned what the graph of that function might look like, the equation of that function might look like, and what it would be called. Before Algebra 1, most of you have only been exposed to linear functions, so this was really most of our first experiences with something that is a function that is not a line. We learned that if the equation has a variable with the highest exponent being 2, it makes a u on the graph, which we called a parabola, and it was called quadratic. If the equation or the function has the variable in a square root symbol, it looks like this graph here, and it's called square root function. Absolute value functions are when the variable's inside the absolute value symbols, and it looks like a V on the graph. And then exponential was when the variable was the exponent, and this is what the graph of a basic exponential function looked like. And you weren't asked to necessarily be able to write all of those, you were just kind of being exposed to what they would look like if someone gave you the equation or the graph and asked what kind of function it would be modeling. From there, we went on to evaluate functions given a value or expression. And so they would give you a function, and they'll either tell you a number or an expression inside of the parentheses, remembering that this just means a function of x, and whenever they replace something inside of the parentheses in place of where x was, they're just telling us to put whatever that is in place of all of the x's in the equation. Keeping in mind, it doesn't always have to be f of x. That's the basic notation, a function of x, but it could also change depending on the scenario. They might also say the cost as a function of the number of days that you stay in a hotel. The income as a function of the number of hours you work at your job. So that is the dependent variable depending on the independent one. This is just another way to write the function notation. And so when they put something different inside the parentheses other than the original variable, we are being told to substitute in the function everywhere that original variable was with the new amount or expression. So for example, if it was just a number, like this example here, f of 3, we would replace all the x's with 3's, follow the order of operations. We would do 3 squared, and then do our operations from left to right, and get 7. If instead of a number they give us an expression, it is still telling us to do the same thing. We're still going to replace everywhere in the equation and the function where it used to be that variable, it's going to be replaced. Sometimes there's not a lot we can do, like this one here. Really, there's no reason to go further. I could, but then I'd have to find common denominators and just go so much further than I really am required to do. So for the purpose of this one, we would be finished. The last example, though, if instead it was a minus 4, there's actually a little bit more that we can do here. When we have this negative out here, it's going to distribute to both terms, and it's going to make it a minus a plus 4. And then when I see a minus 4 squared, I've got to remember that just like we can write 5 times 5 equals 5 squared, this is saying that this is the a minus 4 times the a minus 4. I don't just throw an exponent of 2 on a and an exponent of 2 on minus 4. I actually have to remember that this is saying a minus 4 times a minus 4, and then back from section 1, we have to also use the distributive property. So this goes to both terms, this goes to both terms, and what ends up being the result is a squared minus 8a plus 16. And from here, since we do have like terms, we would combine them. We would have a squared, we have negative 9a's, and we have 21 as the combination of our constants. So in standard form, it should be written a squared minus 9a plus 21. The final task that we took a look at in 3.2 was now interpreting the function if it involved function notation and determining a reasonable domain and range if you were given a scenario or a graph that applies to a real world situation. And so we did the Desmos activity, and we had a couple different examples, but the basis was just now that it's applying to something. If they tell you to put the number in for the variable, we'll do that and work it out regardless of what the function looks like. And then based on what it is representing, we need to determine what are some reasonable x and y values based on the context of the problem. So the example that we did was that we had the rocket being launched. They gave us the quadratic function that modeled the rocket's launch, told us to determine S of 5 and explain what it meant, and based on the problem, the t is representing that many seconds after the launch, so they're asking us to find the height 5 seconds after the launch, and so we plug that into each piece. Each time I saw a t, I would plug 5 in for that. So we had negative 4.6 times 5 squared plus 19.6 times 5 plus 58.8. And a lot of us had a misconception that we could multiply negative 4.6 times 5 and then square it, but that's incorrect. We have to square the 5 before we multiply it by the negative 4.6 because that is order of operations. Exponents come before multiplication. The advice I gave you was to just plug the entire thing into the calculator at once so that you wouldn't make any silly errors trying to do it in separate pieces. So once we do all of that, you should come out with, give me just a moment, negative 4.6 times 5 squared plus 19.6 times 5 plus 58.8. We got 41.8. So that's telling us that roughly 5 seconds after the launch, it is at 41.8 meters. And then they asked us, would negative 4 be a reasonable input? So a reasonable x value. Well, x, here they're calling it t, but our domain is representing seconds. There's no way, unless someone has discovered time travel so far, there's no way we can go back in time. Negative 4 would be negative time. So no, it would not be reasonable. Then we were asked what are some reasonable domains for this function. What is a reasonable domain? Well, we just said that we couldn't have negative values, so the only reasonable domain, or x values here, is from time being 0 all the way until the time where it comes back down and hits the ground. So those x values are roughly between 0 and 6. This is a little bit bigger than 5, so between 0 and 6 is our reasonable domain. And then the range is representing the height, so we've got to think, do we want all these values or do we need to exclude some? So the height, we're not going to have negative height. We're not going to have these negative y values. It's not going to go up and then come back down and go underground or anything crazy like that. So reasonable y values are from 0 until its max height here of 80. So the range would be including 0 to 80. So it's about thinking about what is this actually representing? Can it be negative? Can it be decimals? How far does it go? And interpreting what's a reasonable domain and range. And then that was the end of our 3.2 lesson.